could get a better quality.
Yeah, it's okay.
So can you see my slides?
Yeah, I can see now.
Okay. So okay, so you can hear me, right?
Yeah, right.
Okay, great. Okay, so today I will be discussing about the resilience-oriented operation of microgrids under prevailing and event-related uncertainties. So the content for this presentation is like this. First, I will discuss some backgrounds about, although most of you already know about the microgrids and everything, but still, for those who are not much familiar, I will again try to recap it. And then I will discuss about the what is the difference between resilience and the reliability, because most of the power engineers or electrical side, they talk more about reliability, and resiliency is kind of a new topic, but still it's more related to reliability, and also it has some differences. So I will discuss about that. And then when we talk about the resiliency, there are different stages. We talk about before the event, during the event, and after the event. So there are different kind of operation strategies, like the proactive and survivability oriented operation schemes. So I will be discussing about them. And then there are a lot of uncertainties which are associated with these. Some of them are the prevailing uncertainties, which we call the uncertainties which are related to load, to the renewables, or the market price signals. So these kind of uncertainties, I group them in the prevailing category. And then we have uncertainties related to the events, like when the event will occur, the event occurrence time, that is also an uncertain parameter. Similarly, when the event will finish, the event clearing time, that is again another uncertain factor. So we need to consider those also. And then usually when we make these operation schemes in EMS, the time scale of EMS and the real-time operation or the physical hardware is quite different. So because of this difference, there are some discrepancies, or there is some mismatch. So I will be discussing about that also. And we have tested the algorithm in some real environment also, and we have compared the results. So I will be discussing about that also. And finally, I will talk about a bit about the resilience in the context of EVs, that how we can actually improve the resilience of EVs also when we have some events. So this is a brief outline. I will start with the microgrids. As we all know, microgrids, we define them as a small scale power system, which could have distributed generators and loads. And the major advantage, or the major characteristic of these systems, is they can operate both in grid connected and islanded mode. When we have some disturbance or some problem in the grid side, we can actually isolate them from the grid, and we can operate them in the islanded mode. And then another major advantage of microgrids is they can sustain the penetration of renewables. Because of these two benefits, or these two merits, we can think of microgrids as a natural solution to take care of or to cope up with the problems when we have with the events or some outages. And then we can divide these microgrids into different types depending on the type of loads or the generation they have. It could be AC, it could be DC, or it could be a hybrid of AC and DC. And then I would like to discuss a bit about what is the difference between reliability and resilience, and how they are related together. So when we talk about reliability in power systems or microgrids, we define it as the ability of the power system to provide service to the consumers or the customers during normal conditions or typical power outages. What we mean by typical power outages is a single line fault or a single generation outage, which usually we call N-1 or N-2. These kind of definitions we use to evaluate the reliability of power systems. But when we talk about resilience, we talk about some major scale events, and when we can define the resilience like the ability of the power system to sustain some high scale events. These events, we generally call them low probability, high impact events because their probability is low. They don't occur as frequently as these normal events occur, but their impact is quite high. In case of these small events, I have actually charted down here also. So when you see that in case of these typical power outages, their probability is quite high. They could occur every other day. But the good point is we can predict them easily as compared to these events. And another point is when we have one generation outage or one line fault, the other infrastructure, for example, the communication infrastructure or the transportation or other infrastructure is intact. There is no problem with the other infrastructure. But when we talk about these resilience-oriented events, their event probability is quite low, but their impact is quite high. There could be multiple number of faults, there could be cascaded number of faults, and it's not only the electrical network, but also the other networks like the communication or transportation or even the gas network. They all also could be damaged, or there could be some problem with them also. So these kind of events, we call them low probability, high impact events. And the modern power systems, they are considered as reliable. What that means is they can provide service during normal and some small scale outages without any problem. And we have several standard matrices by which we can evaluate the reliability of the power system. But in case of the resilience, even the modern power systems, they are not capable of sustaining these major outages. So we can say that these power systems, even the modern power systems, they are not resilient, although they are reliable. And another issue is till now, we don't have any universally accepted index which we can use to evaluate the resilience of the power system or the microgrids. So this is some background and why these events are important. As I mentioned, they are low probability, high impact events. But recently, in the last few decades or last few years, the intensity and frequency of these events have increased quite a lot. And a lot of people blame this on the climate change, that because of the climate change, especially the extreme weather events, there have been a lot of extreme weather events across the world when we talk about the last few years. So because of this, a lot of attention is being paid on this topic and a lot of research is going on to make the power systems more resilient. So as I have mentioned before, because of the two main characteristics of microgrid, which is the ability to sustain the penetration of renewables and ability to work in the islanded mode, because of these two traits, we can think of microgrids as a natural solution to these kind of events. But in order to use the microgrids, we also need to prepare the microgrids before the occurrence of the event, so that when there is an event, we are relying on the microgrids. If the microgrids themselves are not prepared, so maybe we cannot get the benefit which we are expecting. So microgrids also need to be prepared. So my main focus is on how to prepare the microgrids for these kind of events. When we talk about the methods which we can use actually to enhance the resilience of microgrids or power systems, broadly we can divide them into two types. The first one is the long-term and the second one is the short-term. So the long-term plans, they are actually event specific. And for example, if we want to prepare our system for an earthquake, our strategy will be different in the long term. And if we want to prepare our system for, let's say, some flood or some windstorm, our strategy would be totally different. So these long-term plans, they are more event specific, and also they need a lot of resource and a lot of time. But the short-term plans, of course, their impact is much more higher as compared to the short-term plans. But they need more resource and they need more time. But in case of short-term plans, they are not specific to a particular event. What the objective of the short-term plans is, whatever we have, we try to maximize its utilization, considering any possible outage. So these can be usually some software programs, or the switching or reconfiguration, or these kind of programs, which we can actually use to maximize the utilization of available resource, to maximize the, let's say, minimize the load shedding, or maximize the survivability of the critical loads during the events. And in case of resilience, if you want to compare in just a visual perspective that how a resilient system should work, when we compare with a conventional power system, here conventional means a non-resilient power system. So initially, before the event, both the systems, they are performing quite well. They are performing according to the required level. But this resilient system, which is the green line here, I'm not sure if you can see clearly green. Anyway, one is the red line, that is the conventional system, and the green one is the resilient system. So the resilient system, it prepares before the occurrence of the event. We call it the pre-event phase. They prepare, and when the event occurs, because this system is prepared, they can withstand the event, but the conventional system cannot withstand, and the performance of the system degrades to a very low level. And in case of these resilient systems, although the performance is degraded, but it's much better as compared to the conventional system. And during this phase, they try to adapt to this system by, let's say, dividing their loads into critical and non-critical, by defining the importance or priority of different loads. They try to maintain the system operation level. And when the event is finished, they recover also much faster as compared to the conventional system, and they come back to the normal operation point very quickly. So this is our desired or expected behavior of a resilient system, which should be when there is some event. And if we divide in the previous figure, here we have divided into different phases. But in generally, for the sake of simplicity, we can just divide them into three phases: the pre-event phase, the on-event phase, and the post-event phase. So pre-event phase is about the proactive scheduling, where we try to prepare our system or the microgrids for any potential event. And in this case, usually we use like some conservative operation methodologies, which are not cost efficient, but our objective here at that time is not cost, that is the resilience of the system. And by considering the resilience, we can revise our original schedules to make the system prepare for future events. And during the event phase, what we do is we try to define different priorities for the loads. Because in case of especially when we talk about these major scale events, they could go long, they could last for quite even few days or go up to weeks. So it's difficult to survive all the loads. So what we try to do is we try to prioritize our loads, and our objective is to maximize the survivability of the critical loads, even at the cost of non-critical loads. And the post-event phase, it is about the recovery. And in this presentation, I will be more discussing on these two phases, and the pre-event and the on-event phase. I will not be much discussing on the post-event phase. Okay, so there are already several studies which have studied these effects or these phenomena. And in the pre-event phase, most of the studies, they have just focused on the feasible islanding. What we mean by feasible islanding is when there is some event, by feasible islanding, we mean the ability of the system to transit from the grid connected to islanded mode without having any load shedding. We call this feasible islanding. So they have only focused more on the feasible islanding perspective. Actually, this is a bit 2-3 years old situation. So I have made according to this. Right now, maybe the situation is a little different. But anyway, this was the situation at that time. So they have more focused on the feasible islanding only. But it is a possibility that we could achieve the feasible islanding, but just after when we come to the islanded mode, we cannot sustain, and even we could go for shedding of critical loads to sustain our system. So that could be one problem. And on event phase, usually some flat or constant or fixed penalty costs are used for most of the optimization algorithms, The problem with that is the decision is up to the optimization algorithm when the algorithm was to do the load shedding within the scheduling horizon. That also could cause some problems. And also in case of these events, it's as I mentioned before, it's not only about the electrical network. Maybe, for example, in some region, they are relying on the gas or they are relying on the coal, which is coming from outside to generate electricity. So maybe that infrastructure is also damaged and you don't have the supply anymore. Whatever you have as a storage, you can just use that. So we need to consider those aspects also. And another biggest issue is, as I have mentioned before also, these uncertainties related to the events, that when the event will occur, that information is quite uncertain and exact estimation is quite difficult. In some cases, we can have some rough approximation or estimation, but in some cases, it's totally almost near to impossible to predict these kind of events. For example, when we talk about some cyber terrorism or some cyber attack, so that we cannot predict anyway. But when we talk about some, let's say, environmental or the weather-related events, some flood or some tsunami, there is some prediction. We have some information on hand, so we can use that. So they have different kind of things. And then the another issue is usually in the EMS level, there are the models, they are quite simplified. And there could be some discrepancies when we really implement the system. So we need to analyze how these two systems, the real hardware and the EMS, they interact and what is the difference between them. So these kind of considerations actually we have done. And from here onward, so this slide is almost similar with the previous one. So here I have mentioned the problems, and this one is we have different solutions for each of these problems. For example, we have not only considered the feasible islanding, but also the survivability of critical loads for next, let's say, n intervals. When we go to islanding, we make sure that we can survive our critical loads for next n intervals. And then we have proposed some dynamic penalty cost. By using this, what we do is we try to shift the load shedding towards the end of the scheduling horizon, because we are not sure when the event is going to finish, so we don't want to do any unnecessary load shedding. And then several realistic assumptions like the interruption of fuel supply, and then the event could go for a longer duration from days to weeks. So this kind of considerations. And then the event occurrence time, especially for the weather-related events, we can use some method which we call the fragility curves. They actually relate the event occurrence with some particular environmental parameter. Let's say we can compare the wind speed to predict the outage of a line or the outage of some distribution pole or something like that. We can predict that. So this kind of information we have used. And then some dynamic bonds for these uncertainties in the prevailing uncertainties, which are related to loads and renewables. And then finally, we have tested the algorithm in some lab scale microgrid system. And then we have tried to see how much deviations are there. So from now onwards, I will be taking this microgrid as an example to show how these methods work or how we have developed different operation schemes. So we have an AC microgrid, we have a DC microgrid. It is actually a hybrid AC-DC microgrid configuration. And the loads, they are in both the sides, in AC and DC side. The loads, they are from level 1 to level n. So level 1 corresponds to the most critical load, and the level n corresponds to the least critical load. And we have energy storage on both sides. And we have renewables on both sides, and then we have dispatchable generators on both sides. So that is the configuration. And in normal case, it operates in grid connected mode, but when the event occurs, we can open the switch and we can operate in isolated mode. So the scheduling horizon for the normal operation mode is T, which is usually 24, so 24 hours. But in the islanded mode, we have considered a rolling horizon algorithm, where I think it's 8 intervals. I think this n is 8. So every 8 intervals, we reschedule our system. The reason for doing this is because we are not sure when the event is going to finish. So we try to reschedule our system in a shorter time as compared to this 24. And the operation interval is also different. In normal mode, we operate in 1 hour, but in islanded mode, in the resilient mode, we operate in 15 minutes. So there is another difference. Here looks like complex, but it's quite simple. No need to worry. So here is just about the energy storage system, the constraints to operate within the SOC bounds. The main part is about the resilience is here. So for each side here, X means either could be AC or DC. So we have an AC-DC microgrid. So that's why I use the X to represent the side of the microgrid. So for each side, we determine the net load we have. And then net load means the load, total load, minus the amount of renewable we have, which is the prediction actually. So based on this information, we try to maintain some level of energy in our energy storage system so that when there is some event, we could be able to feed our critical loads at least for this amount of intervals. And this N, it is actually a decision parameter. It depends on our system configuration, the amount of critical loads we have, the amount of renewables we have, the capacity of the energy storage system we have. So depending on that, we can decide that how much maximum intervals we can survive by using some algorithm like this. And then in the islanded mode, what we have done is, because usually the optimization algorithm, one of the drawback of the algorithms is they can't see beyond the scheduling horizon. If we are optimizing for 24 hours, so they can't do anything for the 25th hour or the 26th hour. So we have tried to incorporate that information also, so that towards the end of the day, they try to maintain some energy in their energy storage system, so that when there is some event at the beginning of the next day, we could survive at least our critical loads. So we have provided some incentive if they maintain that amount of energy, so they get the incentive. If they don't maintain, they don't get. So in this way, the optimization algorithm will try to maintain some level of energy towards the end of the scheduling horizon, which could be used for the following days. And similarly, these assumptions which we have used here are about the available energy, which is actually we transform the fuel we have into energy and then we constrain it into the available energy. But here you can see that this is a kind of deterministic model. There is no uncertainties considered, but in reality, we have several kind of uncertainties, which I group them into two types. The first one, prevailing uncertainties, which are related to renewables, loads, and market price. And then the event-specific or event-related uncertainties, which are the event occurrence, event clearance time. So these kind of uncertainties are there, and we need to consider these uncertainties if we want to achieve or if we want to get more realistic results. So for prevailing uncertainties, as most of you know, there are several methods we can use. Each of them, they have their own merits and their own advantages and disadvantages. So in my case, I have used the robust optimization for realizing most of the prevailing uncertainties because mainly of its computational trackability, which we can use, and because here we are talking about some uncertain and some major outage. So we want to prepare our systems for the worst case scenario. And that is the positive point of robust optimization, that it can guarantee you that even in the worst case scenario, your system is ready to use. So that's why, because of these merits, I have used robust optimization to model the uncertainties. So most of you are aware of them, so I'm not going to discuss more about this. But the second group is the uncertainties related to the event. And I have, as I mentioned a bit earlier, the events, they are of different type. For example, some of the events for which we have some initial warnings, especially from the local meteorological agencies. For example, for some flood or for some tsunami or even for earthquakes also, we have some these warnings. So based on these warnings, we can prepare our systems. And one more issue is these resilient operation schemes, which we are talking about right now. we are talking about the pre-event phase before the occurrence of the event. They are actually economically not efficient. And what that means is the operation cost of the system will be quite increased if you apply these schemes, because they kind of work in a conservative way. So you cannot apply these schemes throughout the year or for several days, because it will reduce ultimately the profit of the system. So that's why we need to have this kind of information, that when we are almost sure, or when we know that the event is going to occur in few hours, so we try to prepare our system before that, instead of preparing throughout the year, or instead of preparing several days or several weeks ahead. So that's why we need this kind of information to predict or to estimate the probability or the possibility of the event. And also there are several ways, but one of the most common method which is used is the fragility curves. What they do is they relate the some particular parameter. For example, in case of the windstorms, we compare the wind speed with the failure probability. So in our case, we will be talking about the line which is connecting our microgrid with the utility grid, that what is the probability with a given particular wind speed, what is the probability that the line will be out, or the, let's say the pole which is connecting our microgrid with the external system, what is the probability that given wind speed it will be out. So by using some historical data, we have some number of failures across different wind speeds. It's a log scale. And by using this information, we can transform them into probability. And let's say when the probability is greater than 75%, we will start preparing our system for the event. And it actually does not only depend on this parameter, it also depends on our system components also. For example, the C rates of our energy storage systems, or the ramp rates of our dispatchable or other generators in the startup time, because it is possible that right now, because of some economical benefit, we are not using our local generator, but we are expecting an event soon. So we need to start up our generator so that we could use it when the event occurs. So these kind of constraints and these kind of constraints we can combine together, and then we can decide when to prepare our system for such kind of events. And another issue is, as I mentioned a bit earlier about also, that is the difference between the EMS and the real hardware. So in EMSs, usually longer operation intervals are considered, which are usually in minutes to hours. And we usually just talk about power or energy, but in the real hardware, things are changing more faster. And they are usually in terms of voltages and currents, which are more dynamic as compared to the energy which we are talking about. And the models for energy storage system or other components, they are also usually simplified models. And more specifically, most of the time, they are linearized model, so that to get more computationally efficient solutions. However, in the hardware, there are several dynamics. There are internal resistance of the energy storage, line losses, and even there could be some delay in the communication or interaction between different entities. So in order to analyze this aspect, we have actually tested our algorithms in some hardware. But before doing that, we have actually simulated different scenarios to understand that what are the possible ways, or what are the different ways through which these uncertainties or these discrepancies are coming. So for that, we have considered these 4 effects: the time leading and lagging effect in case of renewables and loads, the magnitude deviation effects, and the time averaging effect, because in EMS, if we are, let's say, doing 15 minutes, so that is an averaging, we need to average that. And then the combination of these 3. And then later we have tested that system in a small scale hardware in Oxford University, actually. So they have this small scale microgrid system where these 3 are the microgrids, and here are some load and grid. So that a power source and a load, so which serve as a grid to the system. And the configuration is like this. We have the microgrid 2, which is connected to the utility grid, and other 2 microgrids, they can trade power or exchange power with this microgrid, and they can also exchange among themselves. And this is actually a DC system. So this is a little different from what I have shown you. towards the beginning, where we have an AC-DC hybrid microgrid system, because they don't have the AC part. So we have only tested this for DC microgrid. The algorithm and everything was same, just the system was different. So we have tested and we got these results. They look quite tedious, so don't need to worry about this. Just the major point which I wanted to point out is the deviation in the energy storage system, SOC of the energy storage system. So the blue one here, the upper one, that is what was expected from the EMS, and the red one is when we actually tested in the hardware. So this difference was almost 7 to 8% in this case, and it was around 3 to 4% in this case, and it was quite minimal in this case. Because as you have noticed, this second microgrid, it was connected with the utility grid, and the distance between this and this was much higher as compared to this and this. So because of those losses, we can see a higher deviation here, a lower deviation, and a minimal deviation here. Although here someone could, because in the when we estimate the SOC, this difference could be also because of the estimation error also, but right now we just assume that the estimation algorithm is perfect. It's not giving any error. We just blame everything on the EMS here. So we say that all this is coming from the EMS, but in reality, maybe 1 or 2% is coming from the SOC estimation error also. There is also a possibility. And then currently we are using the concept of resilience for EVs also. You might have heard a lot about that EVs can be used to enhance the resilience of power systems or microgrids. But what we are doing is a little opposite way. What we are trying to do is we are trying to enhance the resilience of EVs during outages. Because the problem is in future, it is expected that a lot of EVs will penetrate in the system. And when we have a lot of EVs and we also have this kind of some major outages, so we don't have any source to charge even our electrical vehicles. So we need to devise some methodology so that we can keep these vehicles moving. So for that, in addition to these conventional factors, actually what we have proposed is we proposed an energy storage system inside the charging station so that when there is some outage, we could maintain some energy in our energy storage system, and then we use that energy to survive our EVs. Maybe we can't survive all, or we can't just provide full energy to them, but we define the resilience for EVs and we try to fulfill that requirement level. So for that, we need to firstly determine the optimal size of the energy storage system. In order to determine this, we have considered several conventional parameters like the information related to EVs, what is the maximum number of EVs we have, what is the size of the battery inside each EVs, and the different other parameters. And they are related to their arrival and departure times. And then we have the information of the electrical and the transportation network. And then we have the information of the energy storage system and related to the cost. And then this is the additional portion which we have considered, the stochastic information for resilience. For that, what we have considered is we define the resilience for the electrical vehicles, their ability to move to a nearby healthy charging station. The amount of energy which is required by an electrical vehicle to move from this current charging station to a nearby healthy charging station, we call that as the resilience energy. So we try to maintain that energy in the energy storage system. So when we consider all these, so what should be the optimal size of the energy storage system? And to determine the resilience load, we have actually considered different kind of vehicles. For example, some commercial vehicles, this is actually the arrival time in a residential apartment of some commercial vehicles, some private vehicles on weekdays and private vehicles on holidays. So by using this kind of information and by using the information of the nearby charging stations, if we are currently at charging station A, we try to use the distance information for the nearby all the charging stations within the city or outside of the city, so that when there is some event, we could be able to guide our EVs to those charging stations and charge them at least that much amount of energy, they could travel from here to that healthy charging station, and they can charge there, and then they can do whatever they want, or they can go wherever they want to go. So we have used this information. But another issue here which comes is in case of event, let's say we have stored some energy, or we even have some, we assume that we have some renewables also, some rooftop solar or some wind energy, wind turbines. So we have also this energy storage. So in the future, because there are going to be a lot of vehicles, so we may not be even able to provide energy to all of them. Not fully, not even, maybe we are not able to provide them the resilient energy, which we call to go to the nearby healthy station. So for that, we have to define a mechanism to define the priority among them. Let's say we have 10 vehicles, they all need a recharge, and we just have the energy to give to only 6 vehicles. So how do we choose those 6 vehicles? So for that, we also have done some work, and we have defined actually 3 indexes. The first one is the social welfare. So we will evaluate if we give power or energy to this particular EV, what is the social welfare we are getting. And the second point is the community well-being. So what is the objective of this EV, how much community well-being we can achieve. And the final one is the individual satisfaction. That is, of course, same for all. So how that is, we want to maximize the individual satisfaction for all. And in order to calculate these 3 indices, we have these 5 parameters. The first one is the trip purpose. We will evaluate what is the trip purpose of the particular trip for which they are asking a recharge. For example, are they going for some emergency response, or they are just doing some leisure activity, or they are going for shopping. And then the second one is the occupant types, the EV occupants. Are they some disabled or elderly people, or they are just normal adults, or what? We can make as much as we want, different categories. And then is the departure time, when they need this recharge, do they need as soon as possible, or they are just okay even if we do at the next interval, or what is their preference. And then the 4th parameter is the SOC gap. That means how much energy they are asking and what is their current energy. The difference between these two, we call this the SOC gap. And finally, we have included the customer behavior also. That means are the owners of these EVs, they are participating any DR programs or not? And if they are participating, what is their history? Have they fully followed when they were called or not? So these kind of parameters, different combinations of these parameters can give us different indices for these 3. And then we can use some multi-objective optimization technique to solve these 3 collectively in order to maximize the welfare, or in order to maximize the utilization of the available energy we have for all of the owners or all of the EVs. So this is another kind of research which we are actually working right now on this. So I think, yeah, it's almost done. And so here comes the conclusions. So I have talked about the resilience and the microgrids, and then I have also talked about the resilient operation schemes, which we generally talk about the proactive and the survivability oriented. The proactive, by which we mean before the occurrence of the event, and survivability oriented means during the event. And then I have also talked about how we can model the event-related uncertainties and also the prevailing uncertainties. And finally, I have shown you some brief results also about how the modeling differences in the EMS and the real hardware, they affect finally to the SOC, or finally to what we are expecting and what we are getting. And then I have talked a bit about the resilience of the EVs, which is actually a bit opposite concept of what is normally being used. We are not talking about how to use microgrid or how to use EVs for enhancing resilience. Rather, we are talking about how to enhance the resilience of EVs themselves when we have some outage or when we have some events. So that's all from my side. If you guys have any questions, I am here.
Yeah. So thank you for your interesting presentation. So is there any question for him from the audio?
Yes, I think I have. So thank you for Yeah, a nice presentation. And can you
Thank you.
back to slide A and in the pre-event phase, you mentioned
Slide.
about A.
Okay.
Yes, pre-event phase. So you mentioned about the grid reconfiguration. So that means at the time, if you predict some event, maybe will occur in the system, so you will reconfiguration. So the microgrid will operation in Icelandic mode, right?
Yeah.
So the question is because the microgrid have low inertia or even don't have inertia. So so yeah, maybe after isolating the microgrid, maybe it cannot get the steady state operation. So what is the factor, and so how we can know that after we isolate the microgrid, it can operation and in the steady state?
Okay, so yeah, I think that's interesting question. So what we are doing is we are trying to maintain the energy by predicting or by estimating what amount of load we could have. We have especially the critical load, and let's say if we have renewables also in the system, so we try to see what we are going to get tomorrow from renewables and what is the amount of our critical load, and depending on that we try to maintain, let's say, the SOC of the battery. But your question about this steady state, I think that is more related to the control side. So I have not much expertise on that, so maybe I can't comment on that how we can achieve the steady state after going to island.
Yeah, so I think it's okay. You should consider the power balance, right, between
Yeah,
the
exactly.
power generation and the load consumption, right?
Yeah.
Okay. Yep. Thank you.
Thank you.
I'm Bang from US. I also have a question. Can you go to slide 10?
10. Okay.
The time. Yes, here. Yeah, the scheduling time here. Can you tell a little bit about the time, the interval here? Is it about for one interval? Is just about 1 hour for example? So what the exact time?
Okay, I understand.
Yeah.
Okay, so here actually this is a little messy, I think. Actually here I have combined both the grid connected and the islanded both. So the upper one is for the grid connected mode. So here the total scheduling horizon is 24 hours and each interval is 1 hour.
Okay.
But when we go to island, you can see this. I'm not sure if you can see, there is a box, a yellowish box. So this box is the scheduling horizon for the islanded mode. This is, I assume that this is the point at which the event has occurred. So I bring this down. So here, this horizon is 1, 2, 3, 4. So 4, 4, it's 16. And each interval is 15 minutes, not 1 hour here. So these two are actually different, yeah.
So first you divide into 1 hour interval, and inside that you divide to smaller interval. Okay.
Okay. Yeah. So in normal case, it is the normal practice to do hourly because let's say in the market prices also they are decided based on 1 hour. So that's why we try to follow the market price. But when the event occurs, we try to reduce the operation, try to reduce this interval size so that we can cover more the fluctuations. Let's say right now we only have our local generation and local loads and the renewable. So if we just average for 1 hour, so the probability of error is more higher than we do for 15, or even we go for 5. I think it's more better. And for the reason for reducing this scheduling horizon is here you can see it's 24 hours. Here it is just 4 hours. So the reason for reducing this is because we are not sure when the event is going to finish. So we want to get back to the normal operation as soon as the event is finished. So that's why we try to reschedule as fast as possible.
Okay, thanks. And I have another questions about your optimization. Do you have any thing related to the cost of energy storage system? Because you know that in microgrid the cost of ESS may be the most painful thing when we design the microgrid. So so I have a question here is that the capacities of EMS you use here is about how much, and did you do anything to optimize that EMS capacity?
Okay, so in this case right now, the slide I am on, I have not done the sizing of the energy storage system, but for this case, this one, here I have done this sizing of the energy storage system by considering some parameters, or by considering some limitations or information which we have, or the objective which we want to achieve. So here you can see, here is the cost of the energy storage system. So we divide them into the annual operation and maintenance cost, and storage and the balance of the system cost, and then inside the power components we have the PCS, and then for energy we have the battery cost. So we transform them into annual cost, and then we do this for 1 year actually. So because 1 year can cover almost all the dynamics of different seasons and different days, so holidays and working days and national holidays. So that's why we just did for 1 year. We transform the total life cost 1 year and all this information for 1 year, and then we can determine the size of the energy storage system.
Okay, so from the previous slide, so what the capacities of EMS you choose? You don't do the sizings of EMS, so but you have to choose some capacity, right?
Yeah, that's right. So the capacity, I just choose it based on my the critical loads and the renewable. So let's say I wanted to make sure that my critical loads can survive for at least 4 hours after the event. So I consider all the cases, and I try to find some size which could cover for all these cases. So based on that, I just take one value. I did not optimally decide the value.
Okay, thank you. So we just choose, yeah, okay. Yeah, I think that's my question. Thank you very much for your wonderful presentation and also answers of my question.
Thank you. Thank you.
Hello, is there any other questions? Okay.
Yeah. Hi. Can you hear me?
Yeah.
Yeah. Yeah. I have a question. For this, thanks a lot for your presentation. It's very nice presentation. In the presentation, you mentioned you consider the resilience for EV, and here you just only consider EV in most grid to vehicle, right? So just for EV charge, not recharge for the grid during the disturbance or something like that.
Actually, it's both. It's both.
Okay, so you consider grid to vehicle and vehicle to grid as well?
Yeah, actually, maybe I didn't mention in this slide, but yeah.
As you explained, I can see like you try to optimize or try to provide the EV in case they need to recharge or they need, and based on, I mean, just the suggestion, like if you consider, for example, during that time, some EV online are connected, and then some EV with stay of SOC, right? Stay of charge is high, so you can operate the other side vehicle to grid, and at that time can supply for another EVs in case SOC. Yeah, but if you consider about that factor, Oh, it's fine. Yeah, just have a comment.
Thank you. I think that's a good suggestion. Actually, I was talking about the vehicle to grid. What I was talking is little different from what you are saying, and I think that's more interesting. What you are saying is we can use, for example, we have few EVs. Some of them have higher SOC, so we can use them to recharge the EVs which are having lower SOC, right?
Exactly. Yeah.
Yeah. So I think that's
that factor.
Yeah. Thank you.
Okay. Yeah. Thank you so much.
Thank you.
So, okay, I have one question. Actually, can you explain more detail? How did you model your problem? And for example, which method did you use and which software did you use to solve your problem?
Okay, so I think in most of the cases, all my problems, they are, I try to transform them to mixed integer linear programming or linear programming problems. Because, you know, if it is a non-convex or a non-linear problem, so it's difficult to guarantee its global optimality. So that's why I try to only model using the MILP or the LP. And then most of the time, I think almost, every case I have used Cplex for solving these problems by integrating sometime with MATLAB and sometime with Java or Visual Studio. But anyway, the optimization tool was Cplex.
Yeah, thank you. Yeah, I see.
So what optimization tool you use? Is Java?
I integrate, the tool is Cplex, CPLEX. It is from the IBM. Yeah, it is optimization tool. You can integrate that with Java. You can also integrate with Python, or you can integrate with even Visual Studio or MATLAB. It's quite easy to implement. So because usually the Cplex, it also have its own like the environment where you can code, but for that you need to know the syntax of that. So in order to avoid that, you can, for example, if you are familiar with Java, you can just integrate it with Java as a library, and you can use the syntax of Java. Or if you are familiar with, let's say, Python, so you can just integrate Cplex with Python, and you can code in Python.
Yes. Yeah. And you said that most of your optimization problem is just linear programming?
Yes, linear or mixed integer linear.
Okay, mixed integer linear. So 𝐾𝐬let can also do the 𝐾𝐬let library can also do the mixed integer.
Yes, it can do up to quadratic. Cannot go to the non-convex. If the problem is convex, I think you can solve using Cplex.
And then how about the stochastic optimization? Sorry, because I'm not familiar with the stochastic optimization. So can you tell me a little bit more about that? So how we formulate that optimization and how we show that.
Okay, so in case of stochastic optimization, what we do is, let's say we talk about the renewables. So that is our uncertain parameter. So we try to generate several scenarios. We have one predicted value, and just above and below are using some probability density function. We generate several scenarios. And
I remember that you have some slide on that, right?
I guess I didn't explain about stochastic here. Maybe I explained about robust optimization.
Yeah, robust.
Yeah, this one.
Yeah, this one. Also the same or different?
Yeah, it's different. Robust optimization is quite different from the stochastic optimization.
Oh, so here you don't use the probability density function here?
No, I didn't use that.
Okay, thank you. Yeah, I think you may come back another time to listen about the stochastic optimization.
Yeah, actually that is quite little
and
intensive.
also the applied machine learning. I see in your Google Scholar you have a lot of paper in the reinforcement learning. Yeah.
Yeah, we do with reinforcement learning also. But today, because I haven't applied that for this resilient thing, so I didn't talk about that here.
Yes, I hope you can come back again and present to us about that.
Yeah, I think for that maybe Hai is more suitable candidate. He focuses more on that side than me for the machine learning area, the reinforcement learning.
Okay, thank you very much.
So, is there any other question for him?
Can I have another question?
Yeah, sure.
Yeah, can you back to slide 10? I have a question related with the input for your model.
Okay.
Yes. So yeah, what kind of input? And I think you use some forecasting methods to get the input for your model, right?
Yeah.
So what kind of data? Maybe some historical data, or some you also use some like a real-time measurement data for the forecasting model or something?
For here, we need the load information and the renewable information. That is the forecasted values. Actually, we don't use real time because this is some kind of day ahead scheduling actually. So for that, we can predict, or we can use some forecasting method to predict that what will be the values of load, or what will be the values of renewables for the next day, for each interval, let's say for each hour. So that is the input. And other inputs, of course, are specific to the components. For example, in case of these dispatchable generators, their per unit operation cost, their generation limits, and same for capacity and the charging discharging efficiencies of battery, and these kind of parameters, yeah, we need to define before running the algorithm.
Yes, so but I think with this kind of input, I think the model can predict for 1 day ahead or some hour. But let's say about a short-term scheduling, I think if we have some event or some overload of the transformer, I think with this kind of forecasting, I think we cannot detect the real situation of the grid at the short term.
Yeah, real time, I think, yeah, that's different from this. This is kind of, cannot say long term, but still it's long term when we compare to the real time. Yeah, that's different.
Okay, thank you.
Yes, so is there any other question? Maybe no, so okay, I would like to thank you once again for joining us today. So
yeah, thank you all for listening to me and bearing me. I don't know, maybe somewhere it's night, somewhere it's maybe early morning. So anyway, thank you all.
Thank you,
yeah,
Akhtar.
Thank you.
Very, very wonderful presentation. Useful
Hope we can
information.
meet again in somewhere.
Yeah, I hope so.
Yeah, so maybe we will close our meeting today now.
Okay.
Yeah, so
Thank you.
and
have a good day.
Have a good night. I think you will sleep now.
Goodbye.
Yeah, good night. Good night, Korea.
Yes. Okay, bye-bye.
Yeah,
Bye.
thank you. Thank you. Have a nice weekend.